Welcome back to another episode of Earth is Our Home. Today we're going to be talking about the third installment of Climate Engine. So stay tuned. Welcome back to another episode of Earth is Our Home with Dr. Thomas Blaine, an associate professor with the Ohio State University Extension Program. Tom, it's always a pleasure talking with you. I really learn a great deal about weather, climate change, climate engines, and things of that nature. And I'm looking forward to this episode.
Well, thank you a lot, Patrick. I appreciate you having me. It's always great to come on here and talk about these issues, global warming, global climate change. Together, these are probably the most widely discussed environmental topics of our era. And I hope I'm able to contribute to people's understanding of what is happening with Earth's climate. You can't hear about what's going on globally with climate without hearing about El Nino, La Nina. Essentially everybody's heard of those and hears about those on a regular basis, but there's very little public understanding of what they are. And so what I'm trying to do right now is teach about global circulation, how air circulates around the globe and produces these phenomena, how the jet stream, we've already talked about how the jet stream works and why it's there.
You know, you were mentioning about La Nina and El Nino. I don't know which is better or which is worse.
I will go through what they are, and you can judge whether you're a La Nina fan or an El Nino fan. Okay, how's that? This is part 6 overall of the history of Earth's climate. We did the first 3. We went back nearly 600 million years and talked about climate change, the natural changes, and the changes that are being influenced by humans now. And this one, now we're on part 3 within that of how the climate engine works. Now, last time we did discuss why variations occur to the natural flow of air around the planet, as modeled in the basic Earth's climate system. It was 2 times ago we did the basic climate system, how it works, as if there were no continents, how it would be. You got to walk before you can run. And so we started walking by understanding how the natural flow of air around the planet works. And then last time we put in land features, continents. Land does not heat up at the same rate as water. It heats up and cools down much faster. And the uneven heating of the Earth is what causes wind patterns and storm patterns and all these things. The positions of continents, mountain ranges, they influence the deviation from what would be the natural flow. And we went into that and how these features produce small-scale phenomena like microclimates. We distinguish between microclimates on the one hand and macro phenomena on the other hand, and explain why winds often blow in the opposite direction of what they would ordinarily be doing in the simple model. Again, it's the uneven distribution of land, the uneven distribution of heat that results from where the sun is shining directly overhead and how the continents are distributed that influence and basically cause the climate system to be extremely complex and have an element of chaos to it. I want to talk a little about the equatorial Atlantic and the Pacific. The main thing that we get out of the equatorial Atlantic, or tropical Atlantic, I guess I should say, that affects the United States directly would be hurricanes and tropical storms. And we know that here we are in June. In a couple of months, we're going to be entering into the heart of hurricane season. And we'll see hurricanes come and threaten the Caribbean islands, probably the southeastern United States. Okay. And, those storms tend to be spawned by a region called the Intertropical Convergence Zone, which we've already discussed. We'll take another look at that. In the equatorial Pacific, that does not generate hurricanes that threaten the continental United States because of the flow of air around planet Earth, as we've discussed. The major thing that we get out of the equatorial or tropical Pacific that influences us is the cycle of El Nino and La Nina. Now, that cycle is caused by what's called the Southern Oscillation. Just remember that term. And we're going to get in today. One thing that you need to remember before we go back into this is that ocean currents in the northern hemisphere flow clockwise. So if you take a look at the eastern United States, where's the water coming from? It's coming from the tropical regions. It's going clockwise. We have the Gulf Stream. It flows off the United States East Coast, off the Canadian coast, and heads toward Great Britain. And from there, the ocean current falls down south, goes off the coast of Spain and Portugal, and comes back down toward the equator. That's a clockwise flow. There's one like that in the Pacific. Same thing, Philippines up to Japan, Korea, Alaska, down the west coast of California, and back toward the equator. Clockwise flow. There's a clockwise flow inside the Gulf of Mexico. In the southern hemisphere, it works the opposite. So water comes up off Antarctica, off the west coast of South America, Peru, Ecuador, and it flows along in the tropics out toward the Philippines. And when it gets out there, it dives south again, back toward Australia, and eventually winds up down off the coast of Antarctica. And it's another big counterclockwise flow. These play a huge role. Those are caused by the rotation of the Earth. So we talked about this global atmospheric model, and you can kind of see how the wind flows are associated with the ocean currents I just gave you. If you look in the mid latitudes where you see westerlies off the coast of east coast of the United States, those westerlies are coming up from the southwest and blowing out in that direction. That's the track of the ocean currents also. And then they head toward Europe, and then they come down off the coast of Africa, and then they come north of the equator. You can see the trade winds down there north of the equator, and they wind up contributing to the push of water coming out of the east, moving west toward the Americas. And if you take a look at the Southern Pacific Ocean, you can see the counterclockwise type of flow there. And here are the cells of circulation that we discussed. Anytime you have two cells coming together with air that's flowing up, you're going to get a lot of cooler air as it rises, condensation, and then storms. Where the two Hadley cells meet, where the sun is shining directly overhead, which on average is the equator, you get a lot of storms. You get low pressure. That pressure's low. Then when it comes on around at about 30 degrees on average. Now imagine right now that Hadley cell is moved pretty far to the left because it's summer. The sun is not shining directly overhead of the equator now. The sun is shining directly overhead. We're very close to the solstice, so it's about 23 degrees. And if you would look in there, you would see around 23 degrees, if you interpolate on the graph, that's where the center of that's where the two Hadley cells come together. That pushes the jet stream north, and that gives us our summer. That's why it's hot out right now, and not so hot out in January and February when all those cells are moved way over to our right, and we actually enter into a polar cell. When an Arctic air mass comes down, we get that. So these cells move, and this is what shows on average. So where the two Hadley cells come together and we have all those storms, that's called the Intertropical Convergence Zone, the ITCZ. This satellite photograph shows the ITCZ at a time when the sun is shining slightly north of the equator. So that might be in April or May. And as you probably expect, the ITCZ moves north of this. It peaks out moving north of this in mid to late summer. So all this storm band that circles the planet moves up north in the northern hemisphere summer, and it moves down south of the equator in the northern hemisphere winter. Now, the thing about it is the storms coming off Africa and the storms we see in the Pacific, two different phenomena. And the main reason for that is the size of the oceans. As you can see, it's just not that far from Western Africa to the Americas. Atlantic Ocean, I've transited it many times, but it's nowhere near the size of the Pacific. And that makes all the difference. So what happens is, as we know, the trade winds are carrying the storms off Africa westward. And as the water heats up there north of the equator, all through the summer, June, July, August, by September, that water temperature reaches its peak. There's a lot of energy. And the ITCZ, Intertropical Convergence Zone there, starts to produce large storms. If you look at the red in those are bigger storms than the yellow and the green. But by the time we get into August and September, we're at the peak of hurricane season. And as those storms come across, they can build, they develop into low pressure surface lows that begin to spiral like a giant vortex. That's our tropical storms and hurricanes. remember, there's a clockwise flow. So as the ITCZ gets toward the Americas, those storms start to track off not just to the west, but to the northwest. And that's why hurricanes then strike the Caribbean, those Caribbean islands, and then they come on and strike Florida, the Carolinas, because as they move west, they move north. It's a clockwise flow. All right. Now, if you look in the Pacific, California is free and clear. We don't have hurricanes in California, as you know. Why? Well, I just gave you a big hint. Why? In the ITCZ in the Pacific, you do not have a tendency for those storms in the eastern Pacific to move north because it's a clockwise flow. That means the flow coming down from California is bringing weather and wind and currents from California down toward the ITCZ, not the other way around. So storms don't go against that. So even if you have a powerful storm out there in the Pacific, it's not going to move up toward California. All right. So forget about hurricanes hitting California. And again, it's a property of these ocean currents and also the size of the ocean. Now, another thing that happens in the Pacific, because it's so huge, is we've got almost like a tale of two oceans. In the Eastern Pacific, off the coast of South America, you see that the water tends to be cold. We already know why. It's a counterclockwise flow. So where's that water coming from? It's coming from off the coast of Antarctica. That's pretty cold water. Okay? It's a counterclockwise flow. It then moves along the equator toward the Philippines. As it moves west, it's near the equator, and so it's warming. It warms as it goes. And by the time it gets to the Western Pacific, the water's warm. So you got in the Eastern Pacific, cold water, warm water in the Western Pacific. All right. Notice in the United States, we have the two jets. The subtropical is where the Hadley cell meets the Ferrel cell. As you know, I've told you we live in a Ferrel cell. The polar jet is where the Ferrel cell meets the polar cell. Now, in this scenario here, notice the polar jet's pretty far south and is actually running through Ohio. So this snapshot, if you will, would not be during our summer. It might be a scenario you would see in October, November, maybe even winter. The subtropical jet's down there over the Gulf, the Ferrel cell's in the middle, and then the polar jet is south of its normal position. So this might be October, November, December. It could be anywhere from really October through about March or something like that. But the key to this is to show you the normal situation in the Pacific. Now, let's say we have a high pressure system set up in the Western Pacific. It drives warm water. We've already seen that the water's warmer in the Western Pacific. It drives warm water toward the continent of South America. And as it does so, it starts warming the ocean. It juices the air. You get a low pressure system. This is the Southern Oscillation. And in this one, we are seeing a development of an El Nino. Not only is warm water coming to heat the equatorial Pacific, you see the difference between there and there. It's going to cause a lot more rain, and that rain's going to, those rainstorms are going to spread out. You tend to get drought in Australia, and you get a drought in the Southwest Pacific. And this is an El Nino. And here it is on the top column on a weather map that has isobars. Look at that giant dome of high pressure in the Western Pacific. It's pushing. High pressure means the air's pushing. And low pressure means the air is coming your way. And so look how warm the water is. The orange and red means warmer water. That's an El Nino. What that does is, by covering the equatorial Pacific, which is huge, with warm water, that water's warm enough and it's a large enough area, because as I said, we don't get this phenomenon in the Atlantic. The Atlantic's just not that big, but the Pacific is huge. And so the release of so much heat can raise the temperature of planet Earth a full degree Fahrenheit or more, 1.2 degrees Fahrenheit, which is quite a lot, as we've talked about the context of temperatures. And it can raise it as long as the El Nino lasts. El Nino typically can last 6 months to 2 years. And we would see the weather chart, which is showing upward trends in temperature, not just show that, but there are bumps. And a lot of the bumps that we've said are caused by changes in the Southern Oscillation. A is El Nino, B is La Nina. La Nina, the high pressure sets up in the Eastern Pacific. So it starts driving that cold water that we saw. Remember, the water's cold off the coast of South America. Now, if you get high pressure, you're pushing that cold water and it goes out. And we're in a La Nina right now in June of 2021. It started a few months ago. And that's why the global temperature right now is not very high. The trend is kind of broken down. Somebody could look at that and say, well, there's not really global warming happening because look what's going on. But that's not true. El Nino and La Nina have this effect. You can pause that if you want to study it more carefully. But in this situation, you tend to get drought in the east. Here's a wintertime pattern for El Nino in the United States. What it does in the United States. Notice that we have the two jets. We have a southern jet and we have a northern jet. And in between that, we have quite a lot of warm weather that goes pretty far up, all the way up into Alaska. That's why I was telling you, El Nino tends to warm the planet. If you're looking at planetary data, global data, and you see a spike over a 6 to 12 month period, it's probably El Nino. And look what La Nina does. La Nina causes a big deviation in the jet streams, the subtropical jet and the polar jet, way out in the Pacific. But notice what happens over the continent of North America. The jet streams join. They actually join during a strong La Nina. And that means there's no ferrule cell. The ferrule cell that we saw collapses. So below where the jet streams are together, we've got the Hadley cell, no ferrule cell, just one jet, and then the polar cell. So we've got cold air, cool air above that jet, wet and warm air down below it. So you can see how this influences, and notice the cool there as opposed to the warm in El Nino. Here's another graphic of it. In El Nino, the jet streams tend to stay apart with a giant section of warm air in the northern United States, Canada, up into Alaska. Here's another vision of La Nina. Again, cold air way up there, and the same spot that the warm air was. And see how far this is from the equator? So what happens at the equator doesn't stay at the equator, I guess is what I'm saying. La Nina brings cold air, and it brings a jet stream that comes together, collapses the Ferrel cell. And I want you to look here. Look at May of 2021. Look what's happened over the last 6 months. If you go back to early 2020, that where there was a peak, a little blue way up there at about 0.6 of a degree Celsius above normal. We were in an El Nino. And, you know, January of 2020, that was only about 18 months ago. Look what's happened since then. We shifted to La Nina, and global average temperature has fallen. That's a degree Fahrenheit, 1 full degree Fahrenheit, which is like, you know, 3 or 4 decades worth of warming just wiped out by La Nina. Well, it really hasn't been wiped out. It's been temporarily put on hold. And because of La Nina, when this La Nina ends, we'll go back to trend. But all these ups and downs that you see in the red, for example, if you want to look at the blue, the ups and downs that we have against the trend itself is a warming trend caused by humans putting CO2 into the atmosphere. But the ups and downs are caused almost entirely by the southern oscillation, which is the cycle of El Nino and La Nina.
I think this is a very good explanation, Tom. And I find it fascinating, better understanding the two different La Nina and El Nino. And perhaps we can continue this at our next segment.
I would love to. It's very interesting. It has enormous influences. People wonder how can things that are happening in the equatorial Pacific influence our weather or global weather, but they do, because it's one big giant global circulation, as we've seen in previous episodes.
We're talking with Dr. Thomas Blaine. He's an associate professor with the Ohio State University Extension Program. We thank you for viewing this, and we look forward to our next episode.